Physics 2211 Lab 5, Fall 2023. Introduction. The purpose of this lab is to explore the motion of a vertical slinky and how its physical nature of the slinky affects its descent due to the force of gravity. The results show a strong correlation between the data from our experiment and the data obtained via our computer model, in which the bottom of the slinky remains almost stationary after the initial drop and then accelerates at a constant rate afterwards. On the right, you see a general free body diagram with M representing the mass at the bottom of a slinky, whether that's a tennis ball or, in this case, just the mass of the actual bottom of the slinky. Basically, the bottom of the slinky is originally stationary, as the force of gravity acting upon that point is equal and opposite the tension force within the slinky pulling back up on the slinky. As the slinky falls, neither force changes until the part of the slinky above it drops, and therefore neither force changes for a short duration. Some relevant physics principles in this lab include the position and velocity update formulas shown on the left, as well as the general force of gravity. Force of drag in this model is modeled as b some constant times the velocity squared. On the right, you see a general model of how the experiment should go with the slinky. The initial conditions of this lab are the mass at estimated around 250 grams or 0.250 kilograms, the initial position, which is roughly 0, 0, 0, as well as the velocity around 0, 0, 0. The system in this lab is the slinky itself, while the surroundings is the Earth as well as everything else in the universe. A screenshot of the code is shown here. The blue ball represents the bottom of the slinky in this lab, while the green line represents the path. The bottom of the slinky initially was at rest at y equal to 0, but eventually fell to where it is shown now, once the slinky fully collapsed. This is the resulting position versus time graph of our glow script model. This is a comparison of the tracker position versus time graph and the glow script position versus time graph, with the y-axis representing the position while the x-axis represents time. Both slinkies are originally extremely stable in position up until around 1.717 seconds, in which they both receive an impulse from the rest of the slinky falling and then fall due to the force of gravity the rest of the way. The graphs are very similar. Results of this lab. Because the slinky is not a rigid object, internal and external forces apply on the bottom of the slinky. Slinky, once released, accelerates at a rate of 9.81 meters per second squared, but not every part of the slinky does. The center of the mass of the slinky accelerates at that rate, but the force of tension within the slinky and the force of gravity are equal at every point below its center of mass as it initially falls. It's almost as if a quote-unquote signal that the mass has been dropped has to be slowly communicated down the slinky. Some possible errors that may have occurred in this lab are because the mass of the slinky was an estimate, the impulse upon the slinky, which resulted in a velocity greater than what is done because of gravity, occurred here. Second possible error is the height of the host of this video was estimated to be 1.75 meters for tracker purposes, but that figure isn't exact. And the final possible error is drag may affect the motion of the slinky as well, but because we didn't include the force of drag in our computer model, it was only present in one of the two graphs. This concludes Physics 2211 Lab 5.